This presentation is brought to you by Roberto Dextre Productions from the University of Alabama in Huntsville. An electrothermal propulsion device, known as an arc jet, has been designed and optimized for the purpose of completing a project assigned by the ISE 739 course at UAH. The arc jet has been broken down into three primary subsystems. The propellant flow injection system, including the automated valve and flow meter. This system produces the flow of the propellant through the discharge chamber. The flow meter serves as a way to monitor the flow to ensure desired thrust capabilities are met and to prevent overpressurization in the discharge chamber. The discharge chamber is the next subsystem. With a cathode heating element, this portion of the system heats the propellant gas using thermionic emissions. The last subsystem is the electrothermal converging-diverging nozzle, intended to induce thrust utilizing the thermal energy from the heated gas and converting it into kinetic energy. The first step for this optimization is to understand the relationships between these systems. Based off the subsystem descriptions, the following design structure matrix can be produced. In the figure, the propellant injection system and computer is labeled as 1. The discharge chamber is 2, and the nozzle is subsystem 3. It is apparent that the subsystem 1 provides a propellant flow at a designated flow rate that is injected into subsystem 2. This increases the pressure within the discharge chamber, or subsystem 2, which is fed back into subsystem 1 as a method to determine choked flow. This is the point where flow rate is maximized and ideal nozzle equations of a thruster can be utilized. Subsystem 2 then utilizes the cathode to heat the gas and prep the propellant for subsystem 3. The nozzle then utilizes the thermal capabilities from the discharge chamber and induces thrust out of the system. This thrust is also monitored by subsystem 1 with the assumption that a certain thrust capability is wished to be sustained. Any increase or decrease in flow rate through the nozzle from the chamber has a direct impact on thrust output. Next, we look at the equations of the device, describing the behavior of the system, utilizing characteristics of the subsystems mentioned. Here you can see the thrust dependent on mass flow rate and exhaust velocity. This is assuming an optimally expanded nozzle. The exhaust velocity is dependent on the specific heat ratio of the propellant chosen, the pressure ratio, and the chamber temperature induced by the cathode. The specific impulse is determined using the exhaust velocity and Earth's gravity. The effective exhaust velocity is found using specific impulse and Earth's gravity. And finally, the change in velocity for a given mission objective is dependent on the effective exhaust velocity and the mass ratio. Moving to the MDL framework utilized, the following is a multidisciplinary feasible MDF, nested analysis and design, NAND or NAND. Microsoft Excel was used to set up this framework and iterate until the convergence was found. This can be first understood by reviewing the objective function shown in the system optimizer. The objective function required that the converged value obtained is the mass ratio of the system, which also describes the initial mass and the propellant mass. The purpose is to minimize the initial mass while maintaining the propellant mass constant, allowing a lighter, more compact vehicle. With a lower initial mass, the closer the mass ratio will be to 1.00. This is determined with respect to the given mass flow rate. Once the system fully converges, the iteration process was repeated multiple times while varying chamber temperature and keeping flow rate consistent. Obtaining enough data points on this level can lead to the capability of using a one-dimensional optimization tool. For this case, 3-point quadratic approximation was applied in order to determine the optimal point for the arc jet versus the change in temperature. These tables show the assumptions made on the propellant, pressure, propellant masses, and mission delta V, and it shows the results obtained after the iteration process. Applying the 3-point quadratic approximate induced an optimal temperature of 124 degrees Kelvin, but with the constraints applied, the temperature would be set at 100, which gave the lowest feasible mass ratio of 1.36.